Hi, and welcome to the Thursday video. This video is sort of to review what will be useful to help you with the 4.1 and 4.2 exit ticket. Just so you know that initially when I put it in Schoology, I had it as ungraded accidentally, but I've changed it. It is a graded assignment, so you definitely want to get that done. Also, if you don't know what you're doing in the 4.1 and 4.2 exit ticket on chemical reactions, then you can't do the next exit ticket, which is net ionic equations. So let's go ahead and get started. The first thing I want to do is sort of review what we went over on Wednesday in class, our whole class practice and review, and then we'll go over the questions that people had questions on the 4.1 and 4.2 exit ticket. All right, so this is what we did on Wednesday. And the first question is talking about balanced equations. And what I want you to get from this is, one, how to recognize if an equation is balanced. So remember, you have the same number of atoms on both sides when you do the tally. And in order to figure out how many atoms you have on both sides, you do have to know how to use the coefficients and the subscripts. So we'll look at an example of that later, but that's just one thing to know. The other thing I want you to do in addition to recognizing if an equation is balanced or not, is also recognizing an appropriately balanced equation. What do I mean by that? There are certain rules that we follow in writing balanced chemical equations. First of all, we don't use decimals as coefficients. So if you so choice A would be incorrect because it has decimals as coefficients. All right. The other thing is our coefficients are the smallest whole number ratios possible, meaning that if you look at the coefficients and those coefficients have a least common factor that you can divide all the coefficients by in order to simplify the coefficients, then that's not appropriately balanced, okay? So that's why choice B wouldn't work, because if you look at choice B, the coefficients 6, 4, 2, and 6 can all be divided by 2, so they can be simplified. The equation that is balanced is choice C. So if you do the tally and if you look at the coefficients, they're great. D is not, it's just not balanced. So if you tallied up the number of atoms on both sides, it wouldn't work. Okay, so that is that, and I'll just be helpful if I sort of zoom this in a bit so you can see sort of the choices that we're talking about. All right. So in addition to that, we then looked at writing a balanced chemical equation for the reaction of aluminum nitrate and ammonium fluoride. And this is what your problems will look like in the 4.1 and 4.2 exit ticket, and also net ionic equation. I'm having you practice using names to write chemical formulas. And you learned that last unit. So this is aluminum nitrate, and we're reacting that with ammonium fluoride, so these are two ionic compounds. Now, to get the chemical formula, you need to know the charges of the cation, which is written first, and then the anion for each compound. And remember that the chemical formula, the overall charge must be 0. So starting with aluminum, that's a metal that you find in the periodic table. It's in group 13, so its carbon charge is +3. So you need to know the common ionic charges based on the groups. So group 1 is +1, group 2 is +2. We skip the transition metals. Group 13 is +3, and so this one is +3. Now nitrate is a polyatomic ion. I know it's a polyatomic ion because it ends in 8 or it could end in ite. So if I see that, I know I'm going to look at this table here, and if you look at nitrate, here it is, has a -1 charge. So that gives us a chemical formula for aluminum nitrate of AlNO3. I need 3 nitrates in order for the overall charge to be 0. Ammonium fluoride, we would do the same thing. Ammonium is NH4+. This is found in the polyatomics, has a +1 charge. And fluoride is in group 17. So elements in group 17 have a -1 charge. So I just need one of each in order to have an overall charge of 0. Okay, so that's first identifying what my reactants are. Then we're going to add the reactants together, and we're going to switch partners, so first and last, and then the inner ones switch in order to form our two products, since this is a double replacement reaction. Now finally we're going to balance it. Now to balance double replacement, instead of writing down all of the atoms individually, what we're going to do is we're going to write cations and anions for each one. So aluminum is the cation for the first compound, nitrate is the anion for a second. I just write those down. I keep my polyatomic ions together. NH4 F. All right, I do the same thing on the other side. And then what we're going to do is do our tally, and we will change the coefficients based on what we see there. So let's go ahead and start with aluminum. Aluminum, there's 1 on this side. I have 3 nitrates. That 3 comes from the number outside of the parentheses. That tells me I have 3 of this group. NH4, I only have 1 of that group. Fluorine, I have 1 of those. Going to the product side, I have 1 aluminum. Nitrates, I have to go over here now. I have 1 of those. NH4, I have 1 of those. And then fluorine, I have 3 of those. That subscript, since it's a single atom, single type of atom or monatomic, it's the subscript that tells me how many I have. Okay, so I look at this and I see that it's not balanced. For example, my fluorines, I have 1 on this side and 3 on the other side. Well, I know that's not balanced. So to balance them, what I'm going to do, let's go ahead and start with the nitrates. I have 3 on the reactant side, 1 on the product side. So I'm going to put a coefficient of 3 in front of the molecule that has nitrate in it, NH4NO3. So that's going to change my number of nitrates now. I have 3 of those. And I also have 3 ammoniums. All right, so now I'm looking at this and I say my nitrates are looking good, my ammoniums are no longer looking good, and my fluorides are not looking good. So let's go ahead and do the fluorides. It doesn't really matter which order you do these in. I have 1 on this side and 3 on that side. Well, to get 3 on the reactant side, I put a coefficient of 3 in front. That changes the fluoride to 3, and that changes the ammonia to 3 as well. And if I look at this, now this is balanced. So the key thing for double replacement reactions is make sure that you split them up by cations and anions. So basically keep the polyatomics, anything that you found in this table, keep that together and treat it as its own group. Okay, last example was balancing combustion reactions. So to balance a combustion reaction, first off, I just give you the compound C3H6, so that's the molecule, and I tell you it's a combustion. So you have to recognize that a combustion reaction is going to react C3H6 with oxygen and make CO2 and H2O, since this is a combustion of a hydrocarbon. Okay, so with that being said, once I know that, I go ahead and write down that unbalanced equation. And I did my tallies, number of carbons, hydrogen, oxygens on both sides. And it wasn't balanced, so I balanced my carbon by putting a coefficient of 3 in front of CO2. I balanced my hydrogen by putting a coefficient of 3 in front of H2O, and they're looking good. Now let's see how many oxygens I have on the product side. 3 times 2, which is 6, plus 3 gives me a total of 9. So I have 9 oxygens on this side. All right, so now the last thing for combustion reactions, we always balance the oxygens last. So to balance the oxygen, I look and I see that I have 9 here. I want to get 9 on this side. So to figure that out, I ask myself, well, what times 2, since there's a subscript of 2 there, will give me 9? And the answer to that would be 4.5. So that means the coefficient that I want to put in front of oxygen is 4.5, because if I put that coefficient there, I'll have 4.5 times 2, I'll have 9 oxygens, right? Which is what I want. But remember, we cannot have a decimal. So what we got to do is we got to go back and we've got to multiply all the coefficients. Since this decimal is a 0.5, I'm going to multiply all the coefficients by 2, including that invisible 1 over there. Just like in math, whatever you do to one side, you have to do to both sides. So all these coefficients are going to get multiplied by 2. And when I do that, I get a balanced chemical equation that looks like this. I'm going to write this one in black. So 2 C3H6 plus, that's 9 O2 goes to form 6 CO2 plus 6 H2O. Okay. Oops, sorry about that. Move that up. So 2 C3H6, 9 O2, 6 CO2, and 6 H2O. Okay, so this is what we covered yesterday. So if after looking at this you're good, there's no need to go into part 2 to see the problems that we did in class. If you do want to see the problems that we did in class, then you're welcome to do that as well.